Hi, thank you all for coming. I'll talk about our paper, Asynchronous Consensus Without Trusted Setup or Public Key Cryptography. This is a joint work with Cici, Shengxi, Atsuki, Lingren, and Victor Shu, who is also around. Let's get started. So you're in the consensus session, so we will start with the classic consensus problem. And this is an n-party protocol where T of them could be malicious, and the goal is to agree on a single bit. So pictorially, this is what it will look like. We have n parties. Each of them has a bit. And then they input this bit to a binary agreement protocol, and they receive a single bit output from the binary agreement protocol. And we want this BA box to satisfy some properties. First is the agreement property, which says any two honest parties output the same bit. And it should also satisfy some validity property, which means that if all honest parties input the same bit, then they should output the same bit as well. And we also want that the protocol terminates. So in this paper, we look at a slightly different variant of this consensus problem, which is also known as common subset or the interactive consistency problem. Here, it's again an n-party protocol with up to T failures. But now the goal is to agree on a subset of inputs. So we have parties, and each party has an input. Here, I'll use MI to denote I'll use MI to denote the input of that party, and they provide this input to a common subset protocol, and the end goal is to output a subset of messages, capital M, M1 for party 1, M2 for party 2, and so on and so forth. Now we want, and these messages belong to some of the parties that they provided input to. And we again want some nice properties. First is the agreement property, which says any two honest parties output the same subset of messages. And also we want validity property, which says the set they output contains at least n-2t honest inputs. And also we want the protocol to terminate. This common subset primitive has many applications. So we're in the blockchain session, so the obvious application is the blockchain. But we can also use this for secure multi-party computation. We can also use this for distributed key generation protocol. We want to solve this common subset problem in the asynchronous networks. Let's define what it is. So it's a network model where message delays could be arbitrarily long. But the guarantees you want that the messages must eventually arrive. So pictorially, this is what it will look like. Let's say we have two honest parties. If a party sends a message to the other party, the message can be delayed arbitrarily long by the adversary, but the message must eventually have to arrive. And this is very good to model internet-like network where you don't really have control over the message delays. Okay, so we want to solve this asynchronous subset problem common subset problem in asynchrony. And this is what it looks like. You can imagine we want to solve it for nodes that are running over the internet, do not have a dedicated connection. But here's one problem, that we know that deterministic asynchronous consensus is impossible. And this is a very classic result by FLP. So what do we do? But we have a savior here. The impossibility result says the protocol, it is impossible only if the protocols are deterministic. So we'll rely on randomness. So we know how to construct ACS protocol, asynchronous common subset protocol, which are randomized. So we have the ACS primitive as is. If we feed in some source of randomness, it could be shared randomness, it could be local randomness, we can solve this ACS problem. Okay? So now the problem boils down to how do we build a common coin protocol in asynchrony? And if you have worked in this area, you will know that to build common coin, we rely on ACS. So to repeat, if we want to build a common coin in asynchrony, we use ACS. But here we have seen that if we want to solve ACS, we need the common coin. So we get this circular dependency. And this is why this problem is harder to solve. But fortunately, we know how to get past these impossibility results, and there are many, many results. I'll highlight some of the ones. So these are state of the art, according to me, in the asynchronous common subset protocol that doesn't rely on prior setups. But these get really nice communication cost. I can point, okay. They get really nice communication cost of kappa and cube, and they also have very, very good round complexity. But if you look at what kind of assumptions they use, these are public key crypto assumptions. And we don't want them because they are not secure in the presence of quantum computers. But okay, let's not use public key crypto. Let's try to do information theoretic asynchronous common subset. And indeed, there are works. The state-of-the-art work does achieve an information theoretic asynchronous common subset protocol, but it requires 10 to the 5 communication cost. And also, it can only tolerate n over 4 malicious parties. So it's not optimal fault tolerant. So in this paper, we asked, can we design a post-quantum secure ACS protocol without any setup? And the answer is yes. And this is what we get. We get a protocol which just relies on hash functions, and it achieves communication cost, which is similar to prior ACS protocol with public key crypto, and also get a good round complexity. And the natural question is this protocol efficient? And the answer is also yes. Okay, so we'll now look into some of the constructions. Before that, let's look at some of the background. So one primitive that we'll use is this threshold secret sharing. You might have seen this in some of the talks before. So this is again parameterized by N and T, where we have a protocol. It's a mechanism to share a secret among N parties. So we have a secret. We want to divide the secret into N pieces such that any subset of T plus 1 shares lets you recover the secret, but a subset of T or less doesn't reveal anything about the secret. And this is the classic Shami secret sharing scheme, where we embed the secret as the constant term of a low-degree polynomial, and each share is one evaluation point on the polynomial. What we need is something called verifiable secret sharing, which you can think of is a protocol among N parties to share a secret with the additional properties that parties who receive shares can locally verify that they are receiving valid shares. I won't go into the details of how to construct this, but these primitives exist even in asynchronous setting. Okay, the another primitive we need is called reliable broadcast. This is a very old primitive. So here the goal is we have a broadcaster that wants to broadcast a message M to all the parties. And if we do simple protocols where the broadcaster simply sends the message to everybody, then it won't work, because if the broadcast is malicious, then it can send different messages to different parties, and it may not send some messages to parties as well. So we want to do something special, and we already know how to do it even for short messages, even for long messages. So this is also we'll use as a prior work. Okay. The third primitive we need is something called index gather. So this is an asynchronous consensus protocol, but with a weak agreement property. And we weaken the agreement property to be able to bypass this FLP impossibility result. But to define this property, I need to define this notion of party validation, which says parties can validate each other based on some local action. It just means if I'm a participating party in the protocol, I can see whether what other actions other parties are doing, and I'll have a local state of whether I think some party is valid according to some function. So once I define this party validation notion, I can define the index gather protocol. So this is, again, it's a protocol among N parties, and each party has an input, which is a set VI. And VI is the set of parties party I has locally validated. So this is just a purely local notion of validation. And then they provide this input to an index gather protocol and receive an output from the index gather protocol. These XIs are subset of parties. So each party receives a set XI. So what properties do we want from the index gather protocol? First is we want that the protocol terminates. And the second property we want that each party outputs at least n minus t, or the second property we want is the validity property. It says the output only contains valid parties for some notion of validity that we define in the paper. And the third and crucial property we need is the binding core property. It says when the first honest party outputs from the index gather protocol, there exists a core set that you can define as a function of the intermediate state of all the parties, such that every party will eventually output a superset of this core set. Okay? So I'll probably just give you 10 seconds to look at this again. It just says when the first party outputs, we can define a core set X, which is large enough, and everybody will output a superset of this core set. And this is not a new primitive. If you look hard, it dates back to Canity-Revin 93. So this is a very old primitive. Okay? So once we have all the backgrounds, we can now ready to talk about how to construct an ACS protocol. Okay, so there are many flavors to do asynchronous common subset. I'll look at one particular flavor which uses weak leader election. So this protocol proceeds in iterations, and each iteration has two phases. The first is the random weak leader election phase, which will output a party index I, and then we use this party index I to run an agreement protocol. And then we repeat. Well, the random leader election protocol is weak in a sense that parties might disagree with who this leader is with constant probability. Recall, we cannot solve consensus yet because we haven't used randomization yet because of the FLP impossibility. Okay, so this is a weak kind of agreement property. But the property we get is that when parties agree on who the leader is, and if the leader is honest, then the protocol can terminate. So again, if you can see that we'll do it again and again until parties agree on who the honest leader is, and whenever they do, they will terminate. So this is how a class of ACS protocol works. Okay, and in this talk, I'll just focus on the random weak leader election primitive. Okay, let's design a weak leader election protocol. So this is a simple protocol, I'll say. So we can assign each party a random rank, and we can pick the party with the highest rank as the leader. This is what it will look like pictorially. We have parties. We can assign ranks to each party. Let's say Ri is the rank of the party. We assign them ranks uniformly at random and pick the party with highest rank. Let's say R4 is as our leader. And this is easy with an external common coin. If we have a shared coin, then we can easily pick one leader. But we don't want to rely on external common coin because they already rely on ACS. We have this whole circularity. So we want to do something different. Okay, so let's look at one way to construct a weak leader election protocol without external common coin. And from now, the talk will be a bit more technical for about 5-10 minutes. Okay, so we have parties. So each party locally samples a random secret and will share the secret with everybody using a verifiable secret sharing scheme. Recall, it's a scheme to share a secret among n parties so that T+1 parties can recover the secret. So everybody will do this in parallel. So each party is sampling a random secret and sharing it with everybody. And then each party locally waits to see who all did the verifiable secret sharing correctly. So party 1 will locally wait to see and then collect a subset of parties which it thinks that did the VSS phase correctly. And let's call this set to be P1. Party 2 will also locally collect a set. Let's call this P2. Each party will do that. Note that parties might disagree on what the set is because, again, we are in asynchrony. We haven't run any agreement protocol yet. Okay. Now then parties will put this, the set that they have collected through a reliable broadcast protocol, which is just a protocol to send a message to everybody, the same message to everybody. So everybody will do this in parallel. Then each party waits to locally identify a set of indices which it thinks that did the reliable broadcast correctly. So let's call this set X1. Party 1 will think, oh, party 1, 2, and 3 did the reliable broadcast correctly. Similarly, party 2 will also collect a set, party 3, so on and so forth. Okay? Now, each party has a local set of what they think are the parties did the reliable broadcast correctly. Now, once we have the set, they input the set to an index gather protocol. And the index gather protocol will output a subset of parties. Let's say the index gather protocol outputs the set 1, 2, and 3. And we know, since this is an index gather protocol, when the first honest party is output, there's a binding course that we can define. Let's define this set to be 1, 2, 3, such that every party will eventually output a superset of this binding code. Okay? Now then we can assign ranks of parties as simply the sum of the secret of shares shared by party P, or parties in PI. So a rank of party I is the sum of the secrets of the parties in the set PI. And the intuition is this set PI contains at least one honest party, and one honest contribution of uniform random values, hence the ranks will be uniformly random. And then we pick the party with the highest rank in a local view as the leader. And why it guarantees that we'll terminate in a constant probability, it's because of this exact condition, which says if the party with the highest rank in the highest global rank is part of the core set, and everybody will output a superset of the core set, hence everybody will agree on who the leader is. Okay, this is very crucial. Good. But it turns out, if I exactly do this, this is insecure. So we did all this complicated protocol design just to find out that this approach is insecure. And a concrete attacker can indeed attack the system and keep it running forever by exploiting this fact. It will ensure that the party with the highest rank is never inside the code. And I'll show how to do it. Right now. Okay, let's look at the attack. So this is the protocol as is, nothing changed. So now, once an honest party outputs from the set, when honest party outputs in the gather protocol, it will reveal the shares of all these SIs to derive the rank. Now adversary can see what this SI values locally, and then it will pick a S4 for the malicious parties such that it will eventually get a higher rank than all the other parties. Then, since it controls the network, it will do the following attack that I show in this red box here. It will pick S4 such that S4 leads to highest rank, and then it will do the VSS. It will stall the net communication of all the honest parties. It will rush. It will pick set P4 to be 1,4, do the RBC, and then will control the index gather protocol such that the fourth party is included in the output of index gather protocol of every other party. Now, you can immediately say that this violates this condition that the party with the maximum rank is in the core, because the core is 1, 2, 3. Now the party with the maximum rank is 4, and it's always outside the core. And in this attack, adversary did not exploit any properties of index gather. It just manipulated the messages to do this. And adversary can do this repeatedly again and again. Okay. Good. So how this is addressed in the literature, and one way to fix this is to use public key cryptography, is to use threshold verifiable random function. So we have the protocol as is, nothing changed in this figure, but we change how we derive the ranks. So to derive the rank, we now use we define a secret key, which is the sum of the secrets shared by parties in PI. So KI is the sum of the secrets shared by parties in PI, and then we run a public key cryptography-based threshold VRF protocol to derive the rank. But the problem is we do not know how to build a threshold VRF without using public key cryptography, and that's why this approach doesn't work. But this approach is secure, but it needs public key cryptography. Okay, so we'll look at our approach. What we do? Well, we define a primitive called index cover gather protocol. And this is an index gather protocol with a slightly stronger property, which we call as binding cover. So again, we have parties. Each party have input, which is VI. It's the set of parties that party I has validated. And then they input this, they provide this input to the index cover gather protocol and receives the output. Nothing changed so far. And this is an index gather protocol, so it trivially satisfies the binding core property, which says when the first honest party outputs, there exists a core set X such that everybody outputs a superset of that core set. Okay, so this is same as before. So we introduce this binding cover property, which says when the first honest party outputs, there exists a cover set Y of valid parties such that everybody outputs a subset of these parties. So the index binding core property lower bounds the output of every parties by X, and we're trying to upper bound the output of parties by a set Y. And this is, if you think of the attack, adversary could manipulate the rank because after seeing the honest parties output, it can inject one more party in the output of our remaining honest parties. Now we'll upper bound what the adversary can do by a superset Y to prevent that attack. Okay? And we give a construction of index cover gather protocol with n-cube communication cost. Okay, so now we have this insecure weak leader election protocol. So the only change we have to do is to substitute this index gather protocol with an index cover gather protocol. That's it. And now, by the property, so we have a core set. We have a core set which will be output by this index cover gather protocol, not output, but there exists one, and then there will be a cover set which will also be part of this cover gather protocol. So now if we try to attack this protocol using the previous attack, so we have the protocol as is. Adversary can learn the secrets of parties. It can pick S4, but if the cover set is same as X, 1, 2, 3, then by the properties of index cover gather protocol, the party 4 will never be included in output of any honest party. So no matter what the adversary does for party 4, it won't influence the rank of the parties that honest parties care about. Okay, so this attack is inconsequential. Adversary can do this attack, but it won't harm the protocol. Alternatively, if the cover set is 1, 2, 3, 4, right here, so now the output can indeed have party 4, but we can ensure that if the cover set is 1, 2, 3, 4, then adversary have to fix its input S4 before any honest party outputs from the cover gather protocol. Okay, so let's just to repeat how ACS construction work. They use this iterative phase where we have a weak leader election protocol which outputs the party index I, and then we run an agreement protocol, and then we do repeat. And our main contribution is improving this random weak leader election protocol using just hash function. To summarize, we give an efficient weak leader election protocol using only hash functions. And we also have lots of concrete optimizations of the agreement phase, but those are not important for this talk. And we also give a simple hash-based weak asynchronous basis protocol, which is also described in the paper. So I'll now, okay. So I'll use maybe 5 minutes to talk about the implementation and evaluation. So we implement this protocol out of one of my previous code base on asynchronous DKG. And we use Python for networking and use BLS 12381 field operations for finite field arithmetic. And we evaluate it using up to 128 nodes. And we use 2 baselines. First is the ACS protocol from the prior DKG scheme, because that scheme has the same setup as ours. It doesn't rely on any setup, but uses public key crypto. And we also use as a baseline an ACS protocol from Fin, which rely on an idealized common coin. So the goal of our experiment is to show that our hash-based protocol, although it doesn't rely on public key cryptography, is as efficient or better than the prior public key-based crypto. And also it's not much worse than other schemes which rely on an idealized common coin. But I want to say that these experiments are evaluated on a prototype code base, and there are a lot of scopes for optimization. So let's look at some of the evaluation results. First is the bandwidth usages, which is the amount of data a party will send during this ACS protocol. And we see that we don't send too much data. That's what I just want to say. We also look at the amount of messages parties will send during the ACS protocol. And again, this is we send much fewer messages from the prior ACS protocol with public key crypto, but we send slightly higher number of messages from the idealized common coin-based protocol. Let's look at the runtime, which is the end-to-end runtime of the ACS protocol. So our runtime is better, but our runtime is worse than the Fin protocol. And I would say I would attribute this to a better implementation of Fin. So they have a much better networking library. And if we do, because our bandwidth uses, computation cost, and message counts are almost similar, so I would expect a similar runtime. But we see higher, this is because of implementation. Okay, to summarize, we present an asynchronous consensus protocol using only hash functions. It has optimal fault tolerance. It has kappa and cube communication cost, constant round complexity, and then it's a protocol with very concrete efficiency. There are some nice open problems. One is to improve the efficiency or to prove lower bounds. And the other is better implementation, and I feel that better implementation will help the community in general. If we can have a common framework where we can test all our distributed cryptography or distributed protocol, it will be very nice to have. Finally, I want to end this talk with a poem that Victor wrote about this paper. So I don't want to read the poem. You can read it yourself, and I'm ready to take questions.
We have time for a few questions. You can start lining up. Let me start with the first question. So you started the talk with this hope that this is a quantum resilient algorithm, and you used only hash functions. But these were modeled under the random oracle model. So is this the quantum variant of the random oracle model? And can you tell us a little bit about your proof?
Yeah, in the paper, we're a bit loose about proving actual quantum security. there are two variants of the protocol. One where we assume random oracle. There is other, we can instantiate the protocol with concrete assumption on the hash function. We don't really need random oracle, but we need assumptions which are slightly more than collision-resistant hash function. Yeah.
Got it. Okay. Let's go to the questions from the audience.
Okay, thanks for the talk. I was just curious why you chose to frame your talk as about common subset instead of VABA or agreement, because the latter sounds more fundamental. I don't know.
I would say these both are pretty similar primitive. You can construct one from the other, and there was no particular choice of. If you look at the paper, we build a VABA inside, and then we build a ACS using a VABA. So if you just want VABA, you just don't read some subsections of the paper. But yes, the talk is, yeah.
Hey, thanks for the talk. I had a question on the first slide where you show the common coin construction from VSS, even before you described the attack of party 4.
Okay.
There you showed in the last step the output of the gather protocol.
Yeah.
I think you showed in the slide that every party outputs the same set, 1, 2, 3. It was there, right?
Yeah.
And is that a special case? Because if I remember correctly, the gather protocol, parties can output a superset of the core set. So my question is, what happens in that case? Do they disagree on the leader? And if this was reflected on your benchmarks, because then consensus can take much longer to terminate.
I think I used the example where everybody outputs 1, 2, 3 to be able to later illustrate the attack of including 4. But in the gather protocol doesn't give you this agreement property. It might happen that the output looks very similar to this where some parties are outputting 1, 2, 3 and others are outputting 1, 2, 3, 4. This is allowed. This is possible.
And with the gather protocol, do you eliminate this to some extent?
No, gather. You mean index cover gather protocol?
Yes, yes.
We do not eliminate this. It might be possible that the core set consists of n minus t parties, and the cover set consists of all n parties. Yeah, yeah. Now parties can output anything in between.
Yeah. But we don't have any statistical analysis how often this happens, or?
No, in practice, I think it works pretty fine, but we didn't try to do explicit attacks. Yes. Thanks. Okay.
So two quick questions. One is silly. So the silly question is, I guess, presumably you still need encryption and really hybrid encryption in this, even for the VSS. But so the real question is, so a threshold VRF, okay, that's harder, but in general, hash-based signatures are not VRFs, but if you take a one-layer one without internal certificates, something like one-layer XMSS, then you do get a VRF. So the question is, can you do anything with local VRFs?
Okay, good. So to answer your first question, in the VSS, we do require private channels. And you can ask this philosophical question of how do you instantiate these private channels? You can use symmetric crypto. We can go into this philosophical discussion, but we do rely on private and authenticated channels. And to answer your second question, you are saying this XMSS gives. Okay, good. So to solve ACS, we need to have a common coin that everybody agrees on the VRF output. If you have a local VRF where each party outputs a unique value, but they output different values across parties, then we don't know how to get polynomial communication complexity protocols. There are the oldest protocols, I think, BKR, I guess, they use the local coins, but they need exponential runtimes.
Let's thank Sourav again.